Swayam Prabha. Digital India. Educated India.
Hello everyone. So we'll continue to work out some problems. We worked about 3 problems last time. We'll continue with some more problems. So the problem shown here on the screen is related to probability density functions again. Okay, in fact problem 3 was also related to that. Problem number 4. Let U be a stationary random variable with the following definitions for mean and variance. Okay, so we already knew this. This is the standard definition for the mean and variance for using the probability density function. So the U mean is minus infinity to infinity v times f of v dv, and the variance is minus infinity to infinity v minus U mean the whole squared multiplied by fv dv. Okay. So what you have to show is that the variance of U is U squared mean minus U mean squared. That's what you have to show. So this is a standard property of the variance. We just have to prove it here today. So let's see how to work it out. We have to show that the variance of U is U squared mean minus U mean squared. That's what we have to show. Okay. So we know our standard definitions for the mean and variance. Let's see. I will start with the variance of U, which is integral minus infinity to infinity v minus U mean squared, isn't it? That's the definition of the variance dv. And what I'll do is I'll multiply it out. So I'll have minus infinity to infinity, and I have all these terms that are going to come up when I expand v minus U mean squared, isn't it? I'll have v squared f of v, isn't it? And then I will have minus 2v U mean f of v plus U mean squared, this whole thing dv. Of course, there is an f of v here, and then the whole thing multiplied by dv, right? And now I split each integral. So then I will have minus infinity to infinity v squared f of v dv. That's a separate integral. Minus 2 and U mean can come out because it is a constant. It's the average of velocity. It can come out. And then I'll have minus infinity to infinity v f of v dv. That's my second one. And the third one is integral minus infinity to infinity. Actually, what I want to do here is I want to take the U mean out because that is a constant. So that would be U mean squared minus infinity to infinity f of v dv. This is what I have. All right. So I have minus infinity to infinity v squared f of v dv minus 2 U mean integral minus infinity to infinity v of f of v dv. Okay. So, and then U mean squared minus infinity to infinity f of v dv. Now remember, the PDF will satisfy the normalization property. So integral f of v dv is going to be equal to 1 because of normalization. The basic property of the PDF, integral of the entire PDF from minus infinity to infinity becomes 1. So that becomes 1. Okay. This right here is the definition of the average velocity, meaning the mean. So this right here is U mean. And then I have v squared f of v dv. What is that? What is that? So that is, so any variable multiplied by its PDF, right? Any variable multiplied by its PDF gives you the mean of that, and integrated, of course, gives you the mean of that. So this essentially becomes u squared. U squared mean, that essentially becomes u squared mean, minus 2u mean times u mean plus u mean squared. So I have u squared mean and then I have 2u mean squared plus u mean squared. So this is just algebra now. So u squared mean minus u mean squared. This is your answer. U squared mean minus u mean squared. Okay, so probably the only tricky thing is this term here where you have v squared f of v dv. So that means you are taking the mean of f of v, because any variable multiplied by its PDF, okay, an integral would give you the mean of that, isn't it? So that would be the mean of u squared. I hope this is clear. So that was problem number 4. Let's try problem number 5. Okay, now we are dealing with a problem where we talk about the Navier-Stokes equations and how a velocity is calculated. So let's see. A simple numerical method for solving the Navier-Stokes equations for constant property flow advances the solution in small time steps delta t, starting from the initial condition u of x comma t. On the nth step, the numerical solution is denoted by u superscript nx, which is an approximation for u x n delta t, right? Of course, each time step consists of 2 sub-steps, the first of which yields an intermediate result, and we are calling that u hat of n plus 1 is given by u at n plus delta t times this expression here, which is nu del squared uj at n divided by del xi minus uk n del xk of uj n. The second substep is uj n plus 1 is equal to the u hat that comes from here minus delta t del xj of phi of n, where this is the phi is some kind of a scalar field. Okay, this is your situation. You are trying to evaluate the velocity field, but you are at every time step, but it is evaluated in 2 sub-steps. This is the first sub-step, equation number 7, and this is the second sub-step, which is equation number 8. What are the questions? First question is, comment on the connection between equation 7 and the Navier-Stokes equations. Okay, comment on the connection between equation 7. So how does equation 7 relate to the Navier-Stokes equations? Right? How does it correlate with the Navier-Stokes equation? Okay, let's answer that first. Part 1, right? So if you comparing with the Navier-Stokes equations, okay, the equation that was given, which is equation 7, is the temporal discretization of the Navier-Stokes equations. Okay, it is clearly the temporal discretization of the Navier-Stokes equations, but what is not present here? You will see that there is the viscous term and there is the inertia term. Of course, this relates to the time dependent term, so you're trying to evaluate it at the new time. But what is not there is the pressure term. So equation 7 is the temporal discretization of the Navier-Stokes equations, isn't it? Temporal discretization of Navier-Stokes equations without the modified pressure term. So that is the term that is absent. without the modified pressure term. Okay, so that means you calculate the intermediate velocity without taking into account the pressure. It's only the intermediate velocity, but you are calculating the intermediate velocity without using the pressure. Okay, so that is the answer to part 1. Let's look at part 2. Assuming that u of n is divergence free, obtain from equation 7 an expression in terms of u of n for the divergence of this intermediate velocity u hat. Okay, we need to evaluate what the divergence of the intermediate velocity is. Okay, so this is part 2, and what we need to evaluate is del dot u hat at n plus 1, the intermediate velocity. So if I use equation 7 to substitute in u hat, isn't it? If I use equation 7 to substitute in u hat, what I get is, I'll use the index notation, so del xj, and what I'll have is, I will write it I'll just substitute equation 7 in here. So it will be uj of n plus delta t, and then I will have what? I will have this new del squared uj n del xi, that's the viscous term, and then the inertia term, so it is uk of n, and then it is del uj n del xk, isn't it? This is the inertia term, the second one. This is what I have. Now if I use the derivative to take the derivative of each term separately, I'll have del uj del xj, right, of n, right, plus delta t, and if I take a del xj, what do I get? Right, the different derivatives can be commuted, so then what I'll have is delta t times nu, okay, I'll have del squared del xi, and I'll take the del xj inside, so then I'll have del uj n, of course, del xj, isn't it? Minus, okay, and delta t multiplied by this whole thing, right? I can put a bracket here. And then this inertia term, here is what I do. Okay, so I will have to take del xj of the whole thing. So then I will take del uk of n del xj, that is because I'm taking a del xj of the whole thing, and then multiplied by del uj del xk of n, isn't it? And then there will be one term that is left over because I'm just applying the chain rule, and then it would be minus uk of n del xk of del uj del xj n, because I'm just applying the chain rule, and then close bracket. So I have del xj of uk, remember it is del xj of this whole thing. So I have to apply the chain rule, right? First times the derivative of the second plus second times the derivative of the first. That's why both of these are minus, and then it will be del uk of n multiplied by del xj of this whole thing, and I just commute the derivatives, and that's why I have del xj of uj n. So look at what happens, right? Look at what happens. What I end up getting is this is becoming 0 because it satisfies continuity, because it satisfies divergence. This is becoming 0 because it satisfies divergence, and this is becoming 0 because it satisfies divergence. All I'll have in the end is delta t times minus del uk n del xj and del uj del xk, of course, n. This is what I have. This is your expression for the divergence of the intermediate velocity. This is my answer for part 2. Isn't it? So the question was, obtain from equation 7 an expression for the divergence of the intermediate velocity, and that's what this is. That's your part 2. Now, I hope that is clear. Let's go to part 3. Obtain from equation 8 an expression for the divergence of un plus 1. Okay, un plus 1. So here is what I'll have. This is what I'll have. So this is now part 3. If I want to find out del un plus 1, okay, that would be, now what all I'm doing is I just have to substitute equation number 8 here for the divergence. So it would be del xj, and it would be the intermediate velocity uj hat n plus 1 minus delta t times, remember it is, if I go to equation 8, equation 8, it is right here, delta t times del xj of phi n, isn't it? So it will be delta t times del squared phi n del xj. This is what I have. Okay. So here, instead of the del xj of uj, which coming from part 2, this becomes minus del t, because that is also a delta t, right? Minus delta t, so this expression here, this one right here. So minus delta t del xj of uk of n, and then del xk of uj of n, okay, and then I will have plus del squared phi of n del xj. This is my del dot u of n plus 1. This is my part 3. The first term here on the right hand side, it came from part 2. The second term, of course, comes directly by just taking a derivative of del xj. That is your answer to part 3. Part 4. Hence show that the requirement del dot u of n plus 1 is equal to 0 is satisfied if and only if phi n satisfies the Poisson's equation, which is given by this. Okay, so this will be equal to 0. So if del dot u n plus 1, if this is equal to 0, then that means del uk n del xj and del uj del xk n plus del squared phi n, of course, del xj would be equal to 0. Only then would that continuity be satisfied, isn't it? Only then would un plus 1 satisfy divergence. It would be divergence free. So it would be del dot u n plus 1 equal to 0, which means this expression has to be equal to 0 for that to happen. So that means del squared phi n del xj would be equal to minus del uk del xj n and del uj del xk n. Okay, this is the Poisson's equation, isn't it? If I just write it as a Laplacian operator, it is del squared phi n. The left hand side is del squared phi n, which is minus del uk del xj and del uj del xk. As you can see, this is the Poisson's equation. So essentially, we have shown that un plus 1 will be divergence free only if phi satisfies the Poisson's equation given by this equation here. So that is the answer to part 4. I hope that is clear. So this was a slightly lengthy problem. First, we had to comment on the fact that this equation here, how it related to the Navier-Stokes equations. So it seemed like equation 7. So it seemed like this one did not use the pressure term. But essentially, and now that we have done all the 4 parts, we now realize that this is satisfying the Poisson's equation, or in other words, that phi is a scalar, or it is the pressure. But the pressure is not coming in the intermediate step, in the first sub-step. So here you have u hat n plus 1, which is the intermediate velocity that is calculated based on the first sub-step, and clearly pressure is not in there. So that was the answer to the first question. How does it relate to the Navier-Stokes equations? It is related because the pressure term is absent. In the second step, we had to show that we had to obtain an equation for the divergence of the intermediate velocity. And as you saw, it is not divergence free. The intermediate velocity is not supposed to be divergence free. Why? Because it does not take into account the pressure. So there's some physical significance here. And this is a typical numerical method that is used to solve the Navier-Stokes equations. It's a standard numerical method where you use a first sub-step without using pressure, and the second sub-step you include the pressure. So naturally, the first sub-step where you calculate the intermediate velocity will not be divergence free. It will not satisfy continuity, and we just showed that through the part 2. Part 3, we had to obtain a divergence for the velocity in the final velocity. Now, it doesn't come out to be 0 because it seems to be related to a couple of expressions. And in part 4, we showed that this would be divergence free, and it has to be. If it has to be divergence free, then that phi, the scalar, which we thought was just a regular scalar, has to satisfy the Poisson's equation. So the conclusion is that that phi that you see there is essentially pressure. I hope that is clear. Okay, now let's move on and do the next problem. Problem number 6. So the vorticity equation is given by d omega dt is nu del squared omega plus omega dot del u. Okay, we have seen this equation. This is the material derivative, substantial derivative. This is the viscous term, and this is the vortex stretching term. Remember, it is the vortex stretching term. Show that the vorticity squared, or entropy, which is omega squared, this is magnitude, or omega dot omega, where omega in bold is a vector. So omega dot omega gives you omega squared, evolves by d omega squared dt equals nu del squared omega squared 2 omega I omega j del xj of ui minus 2 nu del xj of omega I del xj of omega I. So you have to derive an equation for the entropy. Okay, now this is what you can do. This is what you can do. You have the vorticity equation, which is d omega dt, and here omega is a vector, is equal to nu del squared omega plus omega dot del u. Okay, now if I write this in index notation, because that is going to be easier for me, so del omega I del t plus, what would I have, right? I would have uj del omega I del xj, right? uj del omega I del xj is equal to nu del squared omega I del xj del xj, and then I would have here omega, it is omega dot del, so omega j del j ui. This is what I would have, del j ui. Okay, or since I've been writing it in the standard form, I will do the same thing here, del ui del xj, like this. Okay, now what I do is I dot product with omega, because remember, I want to get entropy. Entropy is omega dot omega, right? Omega dot omega, which is omega squared. So in other words, it is omega I is omega squared, isn't it, in index notation? So essentially I multiply with omega I. That's what I do. And what I get is omega I del t omega I, just to make the notation simpler. And then I will have uj omega I del omega I. Sorry, I'm making it simpler, isn't it? Del j omega I equals, here what I'll have is nu, I'm multiplying by omega I, del j omega I equals omega I omega j and del j ui, like this. This is what I have. Now I'll do the same thing for a lot of terms, and what I'm going to do is I'll take the omega inside here. Okay, so then this becomes del t of omega I by 2. Because I can take the omega I inside and it becomes omega I squared by 2. So if I take a derivative, omega I squared by 2, derivative becomes 2 omega I over 2. So 2 and 2 get cancelled and I get back omega I. So essentially omega I multiplied in there, if I take it into the derivative, it becomes omega I over 2. Okay, and I'm going to do the same thing everywhere. So uj times del j omega I over 2. I'm getting there, isn't it? Omega I over 2. And then here too, what I do is, I do now, so it's not plus, it's equals. And I'll have a nu, and then one of the del j's, I'll do it like that. So del j times, I will have omega I del j omega I, like this. Okay, bear with me, and there'll be one additional term because of the chain rule, and that would be minus nu del j omega I and del j omega I, like this. Why? Because if I take the derivative of this entire expression here, I'll have to use the chain rule by taking the derivative of this multiplied by this, and then this multiplied by the derivative of this, which is what this term is. Okay, so I'm applying the chain rule, and then the last term would just be omega I omega j del j ui, nothing there. Okay, now this is what I have. Here I will leave this first term as such, so omega I over 2 plus uj del j omega I over 2. Okay, that is fine. And then this first term here on the right hand side, I will again do something. I will write this as nu times del j. What I'll end up doing is I will take del j, and then I'll have a del j, and I'll take the omega I inside again. So I'll have omega I over 2, like this. Then I will have minus nu, there is nothing I can do here, del j omega I and del j omega I, and then the last term also there is nothing I can do, so that is omega I omega j del j ui. This is what I have. Now as you can see, omega I is just entropy. I end up multiplying the entire equation by 2, so then what I'll have is del t omega squared plus uj del j omega squared equals, then I end up multiplying by 2, isn't it? So I will have 2, what ends up happening is I will get nu del squared omega squared, isn't it, minus 2 nu del j omega I and del j omega I plus 2 omega I omega j del j ui. This is what I have, right? So if you compare to what we had earlier, so essentially what I have is this becomes d omega squared dt, isn't it? That becomes d omega squared dt, and then what I have is here what ends up happening is if I end up multiplying by 2, and that's when I get new, so a new del squared omega squared, so that is new del squared omega squared minus 2 new del j omega I plus 2 omega I omega j del j ui. And if you notice, that is the equation I was supposed to prove right here. D omega squared is equal to, so this is the substantial derivative of the entropy, is nu del squared omega squared, isn't it? That is del squared omega squared minus 2 nu del j omega I plus 2 omega I omega j del j ui. That's exactly what I had to prove, and which is what I got. Okay, so I hope that was clear. We'll work out more problems in the next class. Thank you.